All right, so this section is going to cover modeling mass spring damper systems. And there's going to be a four-step process in this class to actually model these systems. So the first step is we're going to select our coordinates and our variables. So independent masses, ones that are not directly connected to each other, should each have an associated velocity, and independent springs should each have an associated deflection. So springs in parallel tend to not be independent. So they would all have the same deflection. And then once we've done this first step, we're going to get a free body diagram for each mass. And we're going to write out Newton's second law. And then once we do that, now we're going to write out our rate of change of deflection for each spring, and then eventually just replace all our variables that the equations of motions, such that the equations of motions are only in terms of velocities, v, deflections, d, inputs and external values like our forces, and the parameters of the system, m, c, and k. And that's all it takes to model a mass spring damper system. So let's kind of go through an example. So this basic example here, we're going to have a spring, a damper connected to a wall, and on the other side it's connected to a mass. That mass has a force applied to it. So for our first step, we're going to assign our coordinates. So this R1 here, that is going to be the location of this spring and damper relative to the wall. So it's going to be fixed. R2 here is the physical location of this mass, these two connections right here, connecting the spring and the damper to it. That mass is going to have a velocity, which I draw with a double arrow here to represent that kind of flow. And then we're going to also assign a deflection to our spring, which is going to be equal to 0 if the spring hasn't deflected at all, or if it's deflected some static amount due to gravity. So now we're going to write out our free body diagram equation here. So we're going to have, if our mass is pulled downward, let's say by that force is going to pull this mass downward, so is gravity. But when we pull something downward, our damper is going to resist by C times R2 dot. Our spring is going to resist by K times R2. That's our restoring force for those two guys. And then we're also going to have a K times our static deflection due to gravity here, which is going to cancel out with gravity. So we just sum our forces here. We get our equation of motion, our Newton's second law for this mass here. And then what we're going to do is assign or try and figure out what our deflection terms are. So we know for this spring that's deflection or deformation is going to be R2 minus R1, because if we increase R2, we're going to increase that deflection. If we were to somehow increase R1, which we can't in this case, but if we were able to, it would actually decrease it. And then we just take a derivative of that to get the rate of change of deflection. And then finally, all we need to do is just put everything together. We know that R1 is equal to 0 always, and R1 dot is equal to 0. Those will never change. R2 dot is going to be equal to V, and therefore we can get that D is going to be equal to R2. Putting all these equations together, we end up with D dot is equal to V, and MV dot is equal to F minus KD minus CV. And that completely models our system. And since V is equal to D dot, we can also write this as MD double dot plus is equal to F minus K times D minus C times D dot, or shift all these terms to the left-hand side of the equation to get a different representation for the system that's equivalent to it. And that is how you model mass spring damper systems.